We continue with polynomial equations and we look at this very important topic about polynomial regression for data fitting. I know I've done a couple of videos, couple of playlists where I've done some kind of curve fitting and things like that. I think that should be under um, scientific computing with Python and of course numerical analysis and all of that. So you can see things like interpolation, extrapolation, regression. I think probably under statistics and all the rest of it. You want to check all of those playlists out to see this. But since we're talking about polynomial equations, it is also important to mention this here again, polynomial regression for data fitting. So our goal here is to understand the idea of fitting data with polynomial curves, see how polynomial regression is built from basic linear algebra ideas, qualitatively explain underfitting and overfitting, learn how to use graphing tools and software, especially Python, for polynomial regression, and work through concrete examples with code. So let's see how this works. The big picture tells us about what polynomial regression is all about. So in many real world situations, right, the relationship between an input variable x, that's the independent variable now, and an output variable y is non-linear, right? So, and the goal of regression is to find a function that best fits the data so we can describe patterns, make predictions, understand trends. In the last video, we got to a point where we're talking about the fact that we can actually do model real life scenarios with when we have data, right? So this is it on an extended level. Like you have a set of data, and then you want to fit that to a polynomial curve, be it linear, quadratic, cubic, quartic, quintic, and so on and so forth. So in polynomial regression, we assume that the relationship between x and y can be modeled by a polynomial. So it can be linear, which is approximately a naught plus a1x, quadratic, which can be approximately a naught plus a1x plus a2x squared. It can be cubic, and it's approximately a naught plus a1x plus a2x squared plus a3x cubed. And it can be degree n, any degree at all, where y is approximately a naught plus a1x plus a2x squared plus all of that plus an x raised power n. So polynomial regression is still linear in the parameters, that is a naught, a1 up to an. So we can use linear least squares methods. So that is the essence of polynomial regression for data fitting. Now, what is the setup like? Data setup and polynomial model. Um, so suppose we have n data points. So you have a set of data point on anything. Maybe you want to find the regression between the physics and math scores of a set of students, and maybe you have 50 students. In that case, n is 50. So suppose you have n data points, x1, y1, x2, y2, up to xn, yn. So we choose a degree n for the polynomial model. So you don't know you choose a degree that you think is necessary. We're going to find out how to choose the right kind of degree, for modeling, for the polynomial regression. So you have y cap equals a naught plus a1x plus a2x squared plus all of that plus an x raised power n. So the unknowns are the coefficients a naught, a1 up to an. So we build a design matrix X by taking for each xi the row 1 xi squared up to xin, so that we now have the big X to be, first row is 1, and then we have x1, x2 up to xn, x1 squared, x2 squared up to xn squared. And then we have all of that until we have x1 raised power n, x2 raised power n up to xn raised power n, like that. And then we have our y to be y1, y2 up to y big N. And a is a naught, a1, an. So we have all that. So all this a naught, a1 you have there. So they are this vector, the column vector a. So in matrix form, that's simply x multiplied by a is approximately y. That is its data setup and polynomial model. And this helps us in coding, for instance. So in 29.3, we now see least squares idea, the conceptual ideas of least square now. So we usually cannot fit the points exactly, especially with noise. So we look for a that minimizes the total squared error. So error a now is now summation from I equals 1 to n of yi minus yi cap all squared equals summation from I equals 1 to n of yi minus a naught plus a1 xi plus all of that plus an xin, then everything squared. So this is what is happening. In matrix notation, we have error a is the norm of y minus xa all squared. So calculus shows that minimizing a, that's assuming things are well behaved, satisfies the normal equations. X transpose xa equals x transpose y. So in practice, we rarely solve this by hand because I mean it can be quite a massive thing to handle. So we let software do the linear algebra for us. But this is the setup. You have the matrix, and once you put things in matrix form, you can easily code it, you know. So, for example, one, let's look at a conceptual idea, a conceptual example one, fitting a quadratic, for instance. So we have data, e.g., time versus height of a thrown ball. So let's say a ball is thrown at time zero and the height it reaches 1.0. It is thrown at one time one and it reaches 2.7. It is thrown at two and it reaches 3.8. It is thrown at three and reaches 3.2. It's thrown at four and it reaches 1.1. Then we suspect a quadratic relationship like y cap is a naught plus a1x plus a2x squared. Then we build it up like this. So we build x to be so all that one, you have 1 1 1 all the way, and then you now have 0 1 2 3 4. Next, you have 0 squared, 1 squared, 2 squared, 3 squared, 4 squared. These are the x's now. And all of that is now equal to 0, 1 1 1 1, 0 1 2 3 4, 0 1 4 9 16. And then y is okay. I was thinking we'd have more. So y is 1.0, 2.7, 3.8, 3.2, 1.1, following this now. So all the 0 0.1, 2, 3, 4, 5 is what you have here. And because we are using a quadratic, that's why we have up to square. If you're using a cubic expression, we then have plus a3x cubed. And then in addition to this, we now have 0, 1 cube, 2 cube, 3 cube, 4 cube, like that, you know. And then we have the fifth result if we're using that. So we can use Python or a calculator to find A naught, A1, A2 that minimize the squared error. So we are basically looking for all these A naught, A1, and A2. And Python comes to the rescue in this situation. So we now have a Python code to deal with this. So first of all, we have Python implementation one, basic polynomial regression with numpy.polyfit. So we can use numpy.polyfit to fit a polynomial of a chosen degree. So we import numpy as NP and import matplotlib.pyplot because we want to show the plot, right? The fit. And then data, we have X is NPRA 0, 1, 2, 3, 4. Data type is float. NPRA 1.0. So you are basically imputing these two data sets, these two data points, right? Data, this column variables, right? X is this, Y is that as arrays. And then we now fit to degree two. So we say degree is two, and the coefficient is we are looking for the coefficients A2, A1, and A naught. So np.polyfit XY degree. So this degree now, you pick it up here. And we are looking for these coefficients A2, A1, A naught. So, and then we print the fitted coefficients, and then we print A naught is this, A1 is that, A2 is that to four decimal places. And then we can then predict on a fine grid X fit. So this is us predicting now. X fit is n lane space between 0, 4 to 100. And then you put the coefficients and then get the X and put the X fit here. And then that can help us get the Y fit. So you have the data points as in X fit here. And then you have Y fit to see how the curve behaves like. Then you can now then plot data and fitted curve. So you have plot the scatter. So for the real data points, X, Y, you have data points. Then for the plot line now. You have x fit against y fit against x fit, which is a quadratic fit, and then x label is x, y label is y. Then the type of polynomial regression of degree two. Then plot legend. You have all of that. So I'll just go ahead and run this. So you should expect that the code fits a quadratic polynomial, prints the coefficients, and plots both the data and the fitted curve. So this is it right here. All right. So we have it. We have 5 points, right? 1, 2, 3, 4, 5. So this is what we have here. So you have the data points and then the quadratic fit itself, right? So, and you see the coefficient at 0.8914. A1 is 2.7271. A2 is minus 0.6643. So I did something like this under my statistics playlist. I did it manually. It was such a tedious process to do, but I mean, I just wanted to demonstrate how the process mathematically, so that when you code it, you have a better understanding of what is even happening with the code. So if you want to increase the degree here, all you just need to do is come here and say degree is equal to 3, and then you run again, and then uh okay, it's like we have a problem here. Too many values to unpack. Okay, the degree 3 is too high for the set of data we have. So let's go back to what we had. Okay, so degree 2 works best for this. When we have all these coefficients, so you can then rewrite this now as 0.8914. 0.8914 plus A1 is 2.7271x, plus A2. A2 is now 0. Minus 0.6643 x squared. So if this is something that works for you, then you can now begin. You can then use that. So let's as okay. Now you have time where something a ball is thrown and then the height it reaches. So if you now want to know the other height, if you now want to know the height it reaches at maybe some time 5 or 6 or maybe at time 3.5, you just substitute 3.5 here. Since you already know A0, A1 and A2, you can get your Y in this case. Okay. So now, having done that, let's talk about overfitting versus underfitting qualitative. Now, underfitting on, I have a whole playlist on machine learning. You want to check that out. I think I have about 60 videos on that. So the idea of overfitting and underfitting comes up under machine learning a lot, and that is what leads us to have something like hyperparameter tuning. So you can check the playlist there, so where everything is well explained. But this we are just looking at it from the angle of polynomials. So underfitting tells you that model is too simple to capture the true pattern. An example is try to fit a straight line, degree 1, to data that clearly follows a curved path. It won't make sense, right? So the symptoms can be you have large errors on training data and new data, and residuals show a clear pattern. That is, the model systematically misses curvature. Then you can also have overfitting on the other hand. Overfitting, model is too complex relative to the amount of data and noise. That causes overfitting. An example is using a degree 10 polynomial to fit 8 or 9 noisy data points. I mean, you can even see that I was using a degree 3 polynomial to fit 5 data points, and it wasn't even working well, right? I mean, yeah, 5 data points. So degree 2 seemed to work a bit. And if we had used a linear fit for this, yeah, it wouldn't have made, I believe it wouldn't have made so much sense. But a degree 2 thing seems to work better, right? So overfitting, if model is too complex relative to the amount of data and noise, then another reason for an example of that is using a degree 10 polynomial to fit 8 or 9 noisy data points. Like I said, the symptoms can be very small error on training data. The curve wiggles widely so to pass closely to nearly every point. So if the wiggling is too much, you can know that there's overfitting. Then you have poor predictions on new data, that's like bad generalization. So this is related to the bias variance trade-off. So the bias variance trade-off is something that comes up a lot in machine learning. So for simple model, yeah, there's high bias and low variance. For complex model, there's low bias and high variance, right? For good model, it balances bias and variance to generalize well. Okay, so then let's talk about overfitting and underfitting in the sense of let's do a Python code to explain the concept of underfitting, overfitting and underfitting like that. So we generate data from a quadratic curve with noise, with noise rather. So y equals 0.5x squared minus x plus 2 plus some noise. Noise is something that is not desirable in your signal. Interestingly, I have a whole playlist or a playlist of 26 videos on spectral analysis. So there I talk about signals a lot. Okay, so here uh, we fit so for to this time we want to fit polynomials of different degrees to understand the whole idea of overfitting and underfitting using Python. So import numpy as NP. We need numpy for numerical calculations, right? Then import matplotlib.pyplot as PLT. We need that to make plots. So if you look, check my playlist on Python basics with EJD, you see I talked about different different Python libraries that you can use for different reasons. And then things like data visualization, you use Matplotlib, Seaborn, and the rest. So here we are generating synthetic data. So you have np.randomSeed. This random seed is to ensure that each time we generate, since you are generating random numbers, each time we generate, we get the same set of random numbers. Because normally, if you don't have that, the random numbers will keep changing from time to time. So here we have XP from -3 to 3 and in 20 divisions. So the true Y is 0.5x squared minus x plus 2. And then we generate some noise randomly. So np.random.normal 0, 1 size is X shape. So it has to follow this shape now because it has to fit into that. Then Y now is the true Y. That this is the real signal and plus the noise that we generated in line 10. So the degrees to compare now, want to look at degree 1, that's a linear polynomial. Then we want to look at a quadratic polynomial, a quintic polynomial that's degree 5, and a polynomial of degree 10. So x fit now will be np.linspace minus 3 to 3 in 400 divisions. Then we now plot the figure size 10, 8. So we now say for I, so we now begin to pick the degrees one after the other. So for I, degree and degree in enumerate degrees start from one. So coefficients, you have np.polyfit xy degree. So we are fitting based on that degree. Then y fit, we have that, and then we plot. So we plot uh for each degree, degree one, degree two, degree five, degree 10, and then we do the plot. So we are going to have, since we are using 4 degrees, so we're going to have a 2 by 2 plot. So we are going to have a 2 by 2 rows, 2 columns of plots, and then x and y label at the data points. Then we plot the x fit and the 0.5 x fit minus x fit the plus, which is the real signal we have, and then the label is the true curve, and then x fit against y fit now gives us label that's degree of fit, maybe degree 1, degree 2, degree 5 or 10. Then the x label is x and the y label is y, and we have polynomial regression for degree, whatever degree we choose in each case. So let's see how this works. So I just run this now, and then in no time we have this coming. So look at this, the first 2 rows now. This one now, so look at the data points. The data points are those circles in blue, and the true curve is what you have here. For the model itself, this is the true curve. For degree 1 fit now, see what you have. Degree 1 fit, we have just a line that doesn't seem to capture all the points properly. But I mean, if you're doing linear regression, maybe that would have been the line of best fit. But then, because of the way the data points look like, it looks like a curve will better do it. So for degree 2 now, you have the data points, and then you have the true curve still there. And degree 2 fit is something, it's a bit close to the true curve, right? At least better than the linear curve. And then when we look at the last two, now look at for degree 5, you have so it's looking a bit better than degree 2, by the way, because I mean, uh, it's trying to touch the point as much as possible. So degree 5 seems a little cool. I mean, probably even a little cooler than the true fit, the true curve, which is in blue dashed lines. But degree 10, you can clearly see overfitting because you see a lot of wiggling to catch up with to touch the points. So you can clearly see some kind of overfitting happening there. So how do we interpret this now? Visually, you see that degree 1 underfits the straight line. So look at degree 1, it's basically underfits the straight line. Degree 2 seems to be close to the true model, as you can see. Degree 2 is somewhat close to the true model. And then degree 5 may show mildly unnecessary wiggles. So of course, degree 5 seemed a bit better to me, but there's some wiggling happening. But degree 10 is totally off. So likely degree 10 likely overfits, following noise too closely. So degree 10 is following the noise too much because of so many obvious wiggling. So degree 2 seems to be closest to what we have. Okay. So now the question is, how do you know which degree to choose when you want to do polynomial regression? So how do we choose the degree n in practice? First of all, you have to do some visual inspection. So you can do a scatter plot of the data points you have. So plot the data, try low degrees like you can first try 1, 2, and 3. Stop when the curve captures the main shape without wild oscillations. Okay. So like immediately we saw this. So this is looking very close to the real thing, right? And then, I mean, this one is also a bit close to it, but then there's wiggling happening, and then 10 is off it already. So stop when the curve captures the main. So degree 2 seems to capture better like that. So train validation split. So you can split data into a training set and a validation set. This is sounding like this is more like what happens in machine learning. So if you check the machine learning playlist, you see a lot of training sets, validation sets, train sets, test set, and validation set, all of that. So you can fit multiple models like degree 1, 2, 3 on the training set, evaluate prediction error. So you can do different degrees and evaluate the prediction error, e.g. mean squared error on the validation set. Then you can choose the degree with the smallest validation error, and then that will be what you go for. So you need some metrics to measure the performance of each fit to know which one you finally settle for. So for cross-validation, a more systematic method for larger data sets can require cross-validation. So you can repeatedly split and average validation error to reduce randomness. And then in this, you also need domain knowledge. So physics might suggest that motion is approximately quadratic. Economics might suggest diminishing returns. And biology might suggest growth curves of a certain shape. Like maybe there's some kind of saturation, like for instance, in chemistry may be talking about saturation in a chemical reaction. Things get to a point and it stabilizes. right? So you want to pay attention to all those key ideas. So the key idea here is that higher degree is not always better. Okay. So once you get a low degree that gives you what you need, don't go for, there's a temptation to go for higher degrees that may not even do a better job than the lower degrees. So beyond this, right, as you can see already, if you try to, I've manually tried to do this whole curve fitting thing under the statistics playlist. It took a lot of time trying to solve manually, but we have a lot of tools that can do all these things for us. So using graphing tools and software, so graphing calculators and online calculators, so tools with and online graphers. Okay, I think I should even remove this. It's like a repetition of what I already have there. So this can go. Okay. So graphing tools and software. So tools we can use include Desmos. I mean, I've been using Desmos throughout this playlist to demo to show you graphs and everything. Of course, at a point we even did curve sketching, but Desmos does a faster job, right? Then there's GeoGebra. I've used it a couple of times, but I use Desmos a lot. Then there are graphing calculators like TI Casio. I used Casio calculator a lot as an undergraduate. Then you can use spreadsheet and software. Spreadsheet software like Excel, Google Sheets, LibreOffice Calc. I've used all of these things, especially Excel. If I have a whole playlist of 45 videos on Microsoft Excel. So I also did things about linear regression there. So you want to check that out too. That's Microsoft Excel with EJD. And then Wolfram Alpha is another one I really like. It's so cool. Like you just take your data points there and you just you see how things work. So before I round off this, I'm going to show you how to use Wolfram Alpha very easily, So typical workflow now, you can enter the X, comma Y data as a table, use the built-in regression or trend line feature. That's in Excel now, or any of these other sheets, any of these other tools. Then you can you can choose polynomial regression and specify the degree, maybe quadratic or cubic. I have that in the Excel theme. Then the software gives you the polynomial equation and coefficient. Then plot the fitted curve together with the data points to visually inspect the fit. I'm going to show you just that. Okay, well, before I go to Python, let me show you how to use Wolfram Alpha for this same thing we did uh, the first data set we dealt with right there. So then we now look at things like R squared to do the fitting. So here now we have you have uh so in Wolfram Alpha you need the things in pairs. So you have 0 against 1.0, you have 1 against 2.7, you have 2 against 3.8, you have 3 against 3.2, and you have 4 against 1.1. That's talking about all this now. So what I'm just going to do is, thankfully, that is coming from Wolfram Alpha. Wolfram Alpha is the CEO is Stephen Wolfram, and they also have this. So I think they made Mathematica, which is such a powerful tool for mathematical computing too. So so here now, all I'm just going to do is I'm going to do, I'll do something like, I can start with linear fit. So the beautiful thing is here is that by the time, as you start clicking on some of these things now, you're going to have suggestions of how to do the procedure. So if you want linear fit, for instance, so you can just click on this. So, and then you put the values in pairs. So like what I talked about the other time, we have, we want to do linear fit for 0, 1.0. So from what we had over there, then we have 1 against 2.7. Okay. And then we have 2 against 3.8, 2 against 3.8. Then we have 3 against 2 against 3.8. Yeah, we have 3 against 3.2, 3 against 3.2. Then we have 4 against 1.1. Interesting. 4 against 1.1. So this is linear fit now. So all I just need to press this equal to sign, and then we have linear function. So all this is plotted for you. So you have this whole thing going on like this. So you have this straight line, and then you want to look. Can we get a metric? Yeah, look at the metrics. Look at for instance, I think we can look at the adjusted R squared, or of course you have AIC, BIC, R squared, and all this, and this is adjusted R squared. So, and it gives you the least squares best fit, which is 0.07x plus 2.2. That is linear fit now. So for linear fit, we have 0.07x plus 2.22 for that set of data. So that's for linear, and the R squared is quite small. It's 0.007. I think R squared should be as close to 1 as possible, I believe. So, but if you don't want linear fit, then you can just come and say you want quadratic fit. Quadratic. So for quadratic, we just press and just press enter when you make it quadratic. Now you have this expression, right? Minus 0.6648. I think this like what we got, there. And you can see the R squared is really very high. It's really high now. So I hope I can expand this. Yeah, thankfully I can expand. So see what I did here, quadratic fit. Okay, let me go back to linear again before I come back here. So I do the linear fit again. Okay, I do the linear fit. I press enter, and then all these just jump out at us. So it just fits everything 1, 1.27. So this gives a linear function, and this is the expression, the 0.07x plus 2.22. So these are the diagnostics, like these are measures to see the performance. So you can decide based on AIC. Is a K criterion or something like that. You have BIC, you have R squared, you have adjusted R squared, and then you have all the plots of the residuals and all that. So obviously, I can already say that if you look at the way the data points are scattered, the data points are looking quadratic in nature, sort of. So, um, I feel that linear has not done justice to it. So I just go quadratic fit. It's pretty easy, quadratic fit, and press enter, and then the job is done again. So you have polynomial of degree 2. So you have all this now. So you now have, see the expression, minus 0.664286x squared plus 2.72714x plus this. So the AIC is now 4.46, BIC is 2.89. The R squared is close to 1, which is what is desirable, 0.983395. The adjusted one is also very good. Okay, and look at the plot of the least squares feet. See what it looks like, and the residuals like this. So this one, I mean, with all these indices, this metric 0.98, that's like a very excellent one. But I mean, if you're still curious, you can go cubic. When I tried cubic in Python, it wasn't. We had a kind of error. So so this is of degree 3 now. See the expression we have. Okay, the R squared still looks good. I mean, the R squared still looks good. And it even feels that it fits better. So the R squared now is 0.99 compared to 0.98 something the other time, right? So this is 0.996. So, maybe this might even be better, but let's be sure. Let me go quadratic again and see what that looks like. Okay. This is 0.98. So it looks like cubic does a better job here as far as Wolfram alpha is concerned. Cubic seems to be better because the adjusted R squared is 0.966 here. So let's do cubic and see. The adjusted R squared here is now 0.98. So it means that the cubic fit seems a bit better. So you have 0.0075 x cubed minus 0.214286 x squared plus 2.08214x plus 0.981429, like that. And you have all these diagnostics, all these metrics, and the curve seems to fit better. And then you look at the residuals. So let me just go and I'm trying to just be curious a bit more. So I go quartic. So if we go quartic, that's degree 4, and look at the expression. R squared is 1. Okay, I mean, I can assure you that this is overfitting already. This should be some kind of overfitting. I want to believe it's overfitting. So data is perfectly fit by 4th degree polynomial. So perfect fit. Well, I don't know. So this may be questionable if you ask people who should know better. This may be really questionable. I mean, it's perfect. It looks good. But okay, let me even go. This is quartic. Now that's degree 4 polynomial. What if I go quintic, degree 5? Quintic. I hope we have that. If you don't have quintic, then yeah, polynomial of degree 5. Okay, we don't have any results. It's not showing anything, like, because that's clearly out of it. So as far as Wolfram Alpha is concerned, degree 5, degree 4 is doing the best job because it gives a perfect fit. Okay, I mean, that's how you can use Wolfram Alpha. There are many other things you can do with Wolfram Alphas. I mean, if you just start typing alone, you can already begin to see you can do matrices, you can invert matrices and everything. It's pretty easy. Matrix multiplication exponential. You can do all kinds of things. So in case you are just seeing this for the first time, you want to try it out if you get to work with data or math or whatever like that. Okay, so we have seen how to choose degrees like that, and higher is not better, like we said. So Python with NumPy and Matplotlib, right? So I've used Wolfram Alpha to demonstrate how you can fit using different degrees of polynomials. So here we are looking at Python with NumPy and Matplotlib. So Python gives more control and is reproducible, which is excellent for teaching, research, and assignments. So Python implementation. So here, now we are now doing a code that is reusable. We are doing a reusable polynomial regression function. Here is a helper function that fits a polynomial and plots data data plus the fitted curve. So in this case, now what we are doing here is we are doing a function that all you just need to do is go and impute your data later and and put the degree you want, and then you get the result you also want. So here now we are so we have a Python function. Once you see def here, in case you don't understand this, you can check my playlist on Python basics with EJD. So once you see def here, in fact, so that playlist I broke the Python concept down into bits, So we got to talk about functions like down to the finest grains. So here, import numpy as NP and import matplotlib.pyplot as PLT. Then we define a function called polynomial regression, taking x and y, and then degree. Then we have the minimum none, x max none, number of points. So the number of points, you have 200. Then you fit a polynomial of the given degree and plot data plus fitted curve and returns the fitted coefficient that is the highest degree first. So it means any coefficient you have, so if you have a degree 3 thing, so the first coefficient you have is A3, and the second is A2, and the third is A1, and then and so on and so forth, right? And then A naught. Then you have the coefficient np.polyfit x comma y degree. If x mean is none, x mean is equal to x dot mean. Then if x max is none, x max is x dot max. Then x fits, you have np dot linspace x min x max number of point. Y fits is np dot polyval coefficient x fit, and then you do the scatter plot of the original data point, and then you do the fit x fit against y fit. Label the degree fit, then x label y label y, then polynomial regression degree, and so on. Then you can return the coefficients. So example usage now, you have x data, talk about NPR is 0, 1, 2, 3, 4. Y data, you have that too. So the coefficient polynomial regression. So in this case, I mean, I can just run this using alternate enter or control enter, and we have this now. Okay. Still talking about that same data set. So in this case now, based on what we saw there, we saw that degree 3 was better than degree 2. Okay. Maybe it was overfitting though. Who knows? Yeah. It seems better actually, you know. Then what if I do degree 4 with the same thing? So that one told us it's perfect because all the lines are touched. So, I mean, this seems to be agreeing with what we did the other time, with what we did on Wolfram Alpha. So degree 4 seems to fit this best. So like 5 points, degree 4 is looking best. So here, this is 0.05. Let me see if it tallies with this. Oh, okay. Can I do Control Z for this? Let me see. I hope I can. Control Z. Yes, this is quintic. So for quintic now, is it also 0.05 like this one is giving us uh oh degree quintic won't work, it's quartic that works, right? Quartic gave us the perfect fit. And Python is telling us the same thing. Quartic fit is it gave us the perfect fit. That's 0.0541. This one is also 0.0541. This is minus 0.50. Minus 0.50. Excellent. This is 0.8458. 0.8458. Wow, that's interesting. They seem to agree a lot. 1.30833. 1.30833. And the last one is 1. Excellent, excellent. So, and that gives like a perfect fit. So you can see the quartic line is touching all the points perfectly, perfectly. So, I mean, going by this, I hope I mean, the fact that it looks this good does not mean that there's no overfitting. But at least going by this thing, the Wolfram Alpha and Python, uh, the aquatic polynomial seems best for the set of data we have. So this function can be reused for multiple data sets and degrees. And if I've done that already, we started with degree 2. I tried 3, I tried 4, and you can see the degree 4 seems to work better than the rest of them. Then we can also have polynomial regression with scikit-learn, which is an optional extension. Scikit-learn is a machine learning thing, straight up. So scikit-learn allows a more general machine learning workflow. So polynomial features, you have linear regression, easy integration with trained test splits, and cross-validation. So you have import number as NP, import matplotlib.pyplot as PLT, from sklearn.preprocessing, import polynomial features, from sklearn.linear model, import linear regression. I mean, I did this a lot, regression, and all those things that machine learning is about is all taken care of under machine learning with EJD. So you want to check that out. 60 videos and all. So I covered every aspect of machine learning. I mean, let me say almost every aspect because I mean there are many other things. But I covered supervised learning, unsupervised learning, and reinforcement learning. I know sometimes people also get talk about semi-supervised, but I covered these key areas of these three key areas. So you can generate the data now, some random data. So you have XP, X, NP lin space -3 to 3, 20 reshape -1, 1, true 0.5. This is like X ravel. This is the signal now. And then you add some noise like we did before. So this is like extension into the realm of machine learning using scikit-learn. So you have the polynomial features, you have the X poly, model is linear regression. So here now, this one has a special tool for linear regression, right? Then you can predict on a fine grid, X feet, line space, -3 to 3, 200. So this 200 makes it finer than what you had before that was 20. And then you do all the plotting like we've been doing all along. And, we get this results now. So here we have a degree 3 scikit-learn fit, which does a better job than degree 2. And if we go by what we learned before, okay, in this case now, how did we choose the degree? Let me see. Or the degree, if the degree was chosen of its own accord, yeah, okay, it's degree 3. Okay. So degree 3, I can easily change it. So if I change it to degree 4, see what we have now. So degree 4 scikit-learn fit comes like this. So I mean, we are beginning to see a bit of wiggle, but this is the true curve which does a better job. So degree 3 seems to be closer to it. So it all depends on what you're working with. What data set? Okay, I mean the data is randomly generated here, so it's not like the same we were working with before. So you can change the degree and all that. So conceptually, this is still polynomial regression, just implemented in a more flexible machine learning framework. So summary of key ideas here that we should pay attention to. So we have that for polynomial regression models, the relationship between x and y using a polynomial. So we have y cap equals a naught plus a1x plus all of that plus a n x raised power n. It is linear in the coefficients a naught up to a n. So we use linear least squares like error a equals norm y minus x a all squared, and the solution satisfies x transpose x equals x transpose y. Underfitting, we have degree is too low, model is too simple, or large systematic errors. Overfitting, degree can be too high, model too flexible, fits noise, and generalizes poorly. So that's what I think was happening when we had that perfect fit with quartic polynomial for those 5 data points. Then the use of this, we can use for visual inspection, train validation splits or cross validation, and domain knowledge to choose a suitable degree. Then graphing tools and software like Desmos, Excel, Wolfram Alpha, Python, Scikit-learn make it easy to fit polynomials, visualize curves versus data, and compare models of different degrees. So having done all of this, you want to use any tool I've mentioned, whether it is Scikit-learn or Python or Wolfram Alpha. You want to use all of them to try your hands on some of those questions. So this one says, given data for the height of a bouncing ball at times this, describe how you would fit a quadratic model using a graphing tool, Python. I mean, we've used this too. I used Wolfram Alpha for this, and we used Python too. So settled. Explain in your words the difference between interpolation and regression when using polynomial curves. Okay, you want to do that. For a data set with 10 points, why might a degree 9 polynomial be a bad idea? Even if it passes through all the points, it might overfit. I think that's the simple thing. Describe practical steps for choosing the degree of a polynomial model using a train validation split. Okay, use Python and NumPy.polyfit to generate data for this with the added randomness, fit degree 1, 2, 3, and 6 polynomial, and so on. In words, explain what it needs to be for a model to have high bias and low variance, and give an example related to polynomial regression. Okay, so we've talked about the model degree being too high, and then the error being too high, and different things like that. So all of this plays into that. So these are questions like, say, how many can we fit into this now? Okay, maybe we can even do everything, right? So try your hands on this. I think it's getting too small. Okay, let me start from maybe 3 and expand. Okay, so we have 3 to 10 at least here. So you can try your hands on all of these things and see how they go. All right, let me know how helpful this is for you. Thank you so much for listening. Let me also know if there's something else you'd like me to try out. If you have subscribed already, I must thank you very much for doing that. If you have not, why not go ahead and subscribe and hit the notification bell also so you can always get alerted each time a new video is released, right? Having done that, you can also um, click on join to become a member of this channel. That gives you some special privileges. Having done that, of course, you also want to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, you want to keep doing maths right. Bye.